Hello, this is Professor Kuehn. Welcome back to my lectures on electricity, magnetism, and light, where we have been discussing the work of Thomas Young, his lectures on light and colors. We've been going through some of the arguments that he's providing that suggest that the wave theory of light is better able to account for the observed behavior of light than Newton's particle theory of light. We got up to about page 238. We were talking about the phenomenon of phosphorescence, which is the second paragraph on page 238. Remember, this is the phenomenon where a substance such as diamond is illuminated with one color of light. You turn the light off, and then that object glows with a slightly different color. And he argued that the wave theory, he thinks, is better able to account for this. I think the argument isn't completely compelling, but you can be the judge. The next thing that he talks about is the phenomenon of what's called stellar aberration. And this is the fact that we'll talk a little bit more about this when we get to the work of Michelson and Morley. But essentially, the stars appear to be in a slightly different position than they are, but not due to refraction of light through the atmosphere, as we came across a bit earlier. Rather, it's because of the motion of the Earth. So, like I said, we'll come back to this more later, but he argues here that the particle theory is very well able to account for stellar aberration, and he argues that the wave theory, properly understood, is also able to account for stellar aberration. Okay, let's move on to the next point, that he talks about the unusual refraction of the Iceland spar, or calcite crystal. And he mentions that, he says that it has been most accurately and satisfactorily described by Huygens on the simple supposition that the crystal possesses the property of transmitting an impulse more rapidly in one direction than in another. So Huygens' theory, according to Young, is able to account for birefringence, but then notice that he goes on to say, it is true that nothing has yet been done to assist us in understanding the effects of a subsequent refraction by a second crystal, unless any person is satisfied with the name of polarity assigned by Newton to a property which he attributes to the particles of light, and which he supposes to direct them in the species of refraction which they are to undergo. So he's saying here that Huygens' theory is able to account for some aspects of birefringence, but not well for others. And he says that Newton claims to have solved this by talking about the polarity of these particles of light. We talked about this a little bit when we were discussing Newton's particle theory of light. And next week when we start talking about how the wave theory needs to be modified in order to account for polarity, we'll have a better understanding of this. But I think it suffices to say right now that, in my estimation, the particle theory is better able to account for the various birefringent phenomena than the wave theory, if you understand the wave theory, as Huygens did, to be compressional waves like sound waves. Once we say that light is a transverse wave, and like I said, we'll come to this next week, once we say it's a transverse wave, then the wave theory is able to completely account for birefringence. But we're not at that point yet. Okay, and then let's talk about, at the bottom of page 238 and the top of page 239, he's talking about the phenomenon of dispersion, where light of different colors is bent by different amounts when traveling through a crystal. So we briefly mentioned this last time, where if you have a prism like this of glass, and you have white light that's shining upon this prism, then what happens is the white light bends into different colors. I'm not going to draw all of them. I'll just draw a couple of them. And let's do a purple one over here. So if you've seen, the front cover of the Pink Floyd Dark Side of the Moon album, you've seen this kind of dispersion of light into different colors when passing through a prism. That is because white light is comprised of all of these different colors. Now the question is, how does the particle theory account for this, and how does the wave theory account for this? According to Newton's particle theory, it's because the particles of light are different size or different mass, so they have different inertia. So the red particles, being the heaviest, are able to bend or go most in a straight line because they have more inertia, whereas the yellow particles are smaller and the violet particles are very small, so they're very greatly affected by the forces that the prism exerts on it. So that's the way that the particle theory accounted for dispersion. How does the wave theory account for it? Well, he argues that the wave theory is able to account for this if you say that the refractive index of the glass, or whatever substance you're talking about, if the refractive index of the glass is itself a function of the wavelength. So the wave theory can account for the dispersion of different colors of light, provided that the refractive index is itself a function of wavelength. And remember that the refractive index is a measure, or provides a measure of the speed of light. Right? Since the refractive index is defined as the speed of light in a vacuum, or in the absence of matter, to the speed of light in that material. So if something has a refractive index like glass of 1.5, that implies that the speed of light in the glass, so this is in glass, is equal to 2/3 of the speed of light in a vacuum. But notice when we do this, we're saying that there's a single refractive index. What he is saying here is that the refractive index actually depends on the color, depends on the wavelength. So red light would have a slightly different refractive index, a slightly different speed than yellow light, than blue light. And that is what accounts for dispersion according to the wave theory of light. Okay, and if we look at, I guess he summarizes this at the bottom of the first paragraph on page 239. He says, "We may therefore consider the pure ethereal medium as analogous to an infinitely elastic fluid in which undulations, waves, of all kinds move with equal velocity, and material transparent substances, on the contrary, as resembling those fluids in which we see the large waves advancing beyond the smaller, or faster than the smaller. And by supposing the red light to consist of larger or wider undulations, longer wavelength, and the violet of smaller wavelength, we may sufficiently then elucidate or clarify, make clear, the greater refrangibility of the red than of the violet light." Okay, so there we have it. What does he do next? In the next couple of paragraphs, he presents what he sees as the most compelling evidence for the wave theory of light. And these are the phenomena of double slit interference and the colors of thin plates. So let me just say one thing about this. I'll probably do a bit more of a lecture on two-slit interference and thin films shortly. But essentially what he's going to argue is that if you were to take this is a two-slit experiment, if you were to take a boundary or a barrier like this, and you were to cut two very narrow slits in it, and you put a source of light back here, so a light source behind the barrier, and this is something that you did in lab already this semester, the light is going to travel through both of these slits. There's going to be light traveling through both of those slits. And if we have a screen over here and look at the illumination of the screen, the interesting thing to note is that we do not have simply two rays of light striking this, as you might expect if light was particles that were traveling through these slits. Instead, you see this interference pattern of red fringes, if it was red light, and dark separations between them. And he argues that this interference pattern can only be explained if light is a wave. That is, if light was a bunch of particles flying through here, you could not have a situation where two light particles coming from slit 1 and slit 2 somehow destructively interfere with one another and cause a dark region and another bright region and a dark region, whereas it's very natural for light waves to constructively and destructively interfere with one another to produce bright and dark fringes. And that's exactly what he's talking about on the next page, page 240, where he's illustrating schematically light traveling through two slits A and B in these wave patterns. And then on a screen over at CDEF, there are locations where the light is constructively interfering and destructively interfering, which produces the bright and dark fringes alternatively. So this is what he's talking about at the end of this chapter. And at the bottom of page 240, he talks about how by looking at the interference fringe pattern and by knowing the separation between the slits, one can work backwards and find out what the wavelength of the light must have been in order to produce that particular fringe pattern. And so he gives us the very first measurements of the wavelength of light here. And this is really seen as some of the most compelling evidence for the wave theory of light. And after Young publishes these results of his experiment that he did, people really start gravitating, so to speak, toward the wave theory of light and rejecting Newton's particle theory of light.